Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to explore the concept of impulse. Now basically impulse is a result of a change in velocity. Now if we just revisit the idea of change in velocity is basically when the speed or the direction of an object changes over time. Now Isaac Newton first put this idea in one of his second law of motion, basically stated that in order to change the velocity of an object, a force needs to be applied upon it. Now, F equals ma is a famous equation that we all know of. Now, change in velocity, as we know, is acceleration. Now, if we then link this together, change in velocity is the same as change in momentum. Remember that momentum is made up of m, the mass of the object, times v, which is the velocity of the object. If we look at change in momentum, it's the mass times the final velocity minus the mass times the initial velocity. So as a result, a change in velocity will also cause a change in momentum, and this has to occur due to the imposition of a force. A force has to be applied on that object to change or accelerate the velocity of the object and thus change the momentum. But not only is the force important, but also the time that that force is applied on the object. So for the same type of change in momentum, a small time will result in a large force, and likewise a large time will result in a small force for the same, as I say, change in momentum. So as a result, this combination of F, force, and T, time, is termed impulse. So impulse equals the change in momentum. So let's just see mathematically where all this comes from. Well, we know that Newton's second law is F equals ma. Force equals mass times acceleration, where acceleration is a change in velocity. So acceleration, as we know, is delta v over delta t, change in velocity over a change in time. So let's link and substitute this into F equals ma. We get F equals the mass times the change in velocity over the change in time. Well, you notice there we've got mv. mv is momentum. So if we rearrange this, we get F times the change in time equals m times the change in velocity. As a result, we get Ft equals the change in momentum. So as a result, impulse equals the change in momentum. And there's your algorithm at the bottom there. So as I stated, impulse is a combination of both force and time. So if t is small, then the change in momentum will produce a large force. And if t is large, then a small force is applied. Let's look at an example where this can be applied, and you can get the idea as to how this all works together. So what I've got here is a video of, it's actually me doing a taekwondo grading, and here I'm going to be breaking 4 concrete roofing tiles with my fist. So here what we're doing is we're lining up the strike, so we go on a nice straight line through the front two knuckles. Okay, so always pleasing to see that when it breaks through. Now you'll notice that there's no pain on the hand. There was no damage to my hand at all. There's my hand. This was only done the other week, so there was no damage that was actually done to the hand itself. So the question is, how is it that I am able to break through solid concrete with just flesh and bone? Well, basically, there are no tricks into this at all. It's all down to basic physics. Now, what we're trying to do is to impart a very, very small amount of time to cause a massive change in momentum, which is going to cause a large force to be generated. Now, what has been noted and has been tested, that your hand, preferably about 4 to 5 kilos of mass, can be accelerated very, very quickly. Now, the hand is in contact with the tiles for a very, very short space of time, approximately about 5 milliseconds of time. Now, with training, what can happen is approximately 2,800 newtons of force can be applied by the human hand. It takes about 2,000 newtons of force to actually shatter 1.5 mils or 1.5 inches of concrete. So you can see if you can actually get short amount of time to change the momentum of the object, we will get a large amount of force. Now that force is implied into the actual structure, causes a lot of vibrations, and as a result it breaks. Now boxers work on the idea they can accelerate their hands very, very quickly. They can change the velocity of their hands very, very quickly, and as a result this is spread over a large area. Now for a boxer, what they work on the idea is jarring the head. They're looking for those knockouts. But for a martial artist, what we're looking for is pinpointing all of that force to go through a specific point. You saw while I was lining up, trying to get my arm nice and straight, so we're going to go straight through the center of the concrete tiles. Now, if we're breaking boards or what have you, it's all about trying to push through as quickly as possible. The quicker you do it, the more force is implied over the object because we're changing that momentum. So hopefully that makes sense. Let's try and look at it on a different manner where it's a little simpler to deal with. So here we've got a car which has crashed into a brick wall. Now the momentum in this case, I just made up these figures, but we're changing the momentum from 100 kilometers per hour to 0. Now this happens when it hits a brick wall incredibly quickly. The result is you can see the damage which is done to the car. A huge amount of force has been applied onto that car, and as a result you can see the damage which has been generated. Now let's take a hypothetical situation where a car has gone through a loose hay bale. Now we're going to get the same change in momentum if it's going to stop from 100 k's down to 0. The thing is that because we're in this hay bale, it's harder to drive, so the result is there is a larger amount of time. There's a larger amount of time to produce the same change in momentum. The result is there's a smaller force, and as a result there's smaller damage. This is why when you see at a racing circuit, they'll put tires around the corners, or if you're going on an intersection on the freeway or a motorway, you'll see their large barrels of water there, or special bumpers. They're there to actually increase the time of a collision, and as a result produce less force or damage onto the car. If we look into the car itself, we've got airbags. Airbags are there firstly so that you don't hit a hard object with your head, but also it increases the time before there is a collision, so there's less force which is going to be applied on your body. Your momentum, your change in momentum is going to be the same. You're going to go from whatever speed you're going to stationary, but if we can increase the time, the result is there's less force. Less force means that there's less damage. So, as I say, we've got airbags, we've got bumpers on our cars. There's a variety of different ways in which we can actually increase the time, so there's less force and less damage. Now, impulse can also be calculated in the mathematical sense using the area of a force versus time graph. So here we've got a force versus time graph. Now, it's a hypothetical force versus time because really all the lines are nice and straight. We would never get that in reality. They would change and they would curve. But for this scenario, basically what we're going to be working on is nice straight lines. So we've got a linear motion between force and time. Now, in order to calculate the impulse as we know is force times time. Well, if I wanted to do this on this object, basically I'm looking at the area under the graph. So you can see I've got a triangle here. So by doing force, which is basically going to be the height of the object, times time, which is going to be the base of the object, divided by 2, that gives me the area. The area of the force versus time graph will basically give me the impulse. So this is the basic setup where we've got force and time, which is imparted. Now, just thinking on a sporting field, if you were playing baseball or cricket and you get a nice hard bat, what you can then do is actually get force being really, really big because the time on the bat is very, very short. So you get a change in momentum, so you get a huge amount of force which is going to be generated, which causes that change in momentum, which is really, really good. This is why there are laws about you can't have it too hard, otherwise you can generate this huge amount of force and impart a really, really big momentum on the object. This is also true in tennis. If you think about the strings, the tension on the strings, basically if you've got soft strings, then the ball is going to be in contact with the strings for longer. As a result, there's less force, and as a result, there's less change in momentum. Or if you get them really tight, the result is there's more force because there's less time on the ball, which causes a greater change in momentum. So all these things can be imparted into an object, and the result is we're always trying to increase the time or decrease the time, depending on what we want to do. Okay, well, let's have a look at an example. So here we've got a 500 kilogram car which is traveling at 12 meters per second. 4 seconds later, its speed is going to change to 16 meters per second. We've got to calculate the change in momentum of the car, the impulse of the engine force, and we're going to calculate what the engine force is. So first off, we're going to calculate the change in momentum. So the change in momentum is the final momentum, mv, minus the initial momentum, mu. So we get 500 times 16, which is our final, minus 500 times 12, which is our initial, which is 8,000 minus 6,000, which gives me 2,000 kilogram meters per second. Now, the impulse is going to be exactly the same because we know that impulse equals change in momentum. So as a result, Ft will equal 2,000 kilogram meters per second. Or this can also be written as Newton seconds because kilograms meters per second is mass, kilograms, meters per second, which is acceleration. So F equals ma equals newtons. So but as a result, we get a Ft can also be written as Newton times seconds. All right, so let's look at the final one where we've got to calculate the engine force. Well, we know that the impulse Ft equals 2,000 kilogram meters per second. So the change in momentum, the force will be the change in momentum divided by the time. Now we know the time that the force was applied on the object was 4 seconds. So we get 2,000 divided by 4. So F is going to equal 500 newtons. Cool. All right, well, let's try this one where we're going to be looking at a graphical situation where we're going to be working out the impulse and then the final velocity for a 57-gram ball which was struck by a racket, noting that the 57-gram ball was initially stationary. So basically we've got the ball, it's stationary, and then we hit the racket and we see what's going on. So area under the graph will give us the impulse. Now you can see that the graph is curved, so what we've done is use the dotted line to basically make it easier, and we're going to calculate the area, which is the height, times the width, and noting that the time is in milliseconds and that the force is in kilonewtons, so it's times 10 to the 3. So we know that the area is base times height divided by 2. Now the base is 3.2 times 10 to the negative 3, and this has been calculated or read off the graph, and we know that the height is 2.5 times 10 to the 3, noting it's kilonewtons, and the whole lot is divided by 2. So the final answer there is 4 Newton seconds. So from there we're going to calculate the final velocity. Well, we know that the impulse, Ft, is going to be the change in momentum. Now you can see here I've just taken out a factor of the mass, so we've got mass times v minus u. So it's the same thing, that's still the same change in momentum, and we know that Ft equals 4 Newton seconds. So we know the mass because it's 0.057 kilograms, converting it from grams to kilograms. We don't know v, and we know that u is 0 because it's stationary. So if I substitute all that in and rearrange, I make sure that v is 7 meters per second. Okay, well, I hope that's been useful on dealing with impulse, and I look forward to you joining me again. So bye for now.